Okay, SETI, the method and science of it. History and method and science. When I was researching this talk, my ideas about it evolved quite a bit. The trouble with a subject like this is that you can end up reciting a whole lot of really, really interesting technical information, which is interesting to the people that it's interesting to. And the rest of the people will fall asleep. And even I started to fall asleep while I was doing it. So I thought, well, that's not a good start, because it is something that I'm interested in, because it's a kind of a sophisticated form of communication. And one of my hobbies is amateur radio, which has turned out to be rather more useful than I had ever thought it would be. And that involves the details of communication in various ways, the channels of communication. And those communication channels are usually, well, where amateur radio is concerned, they're usually radio, but not always. There's also communication between computers and radios, and interfacing, hybrid communications with internet, radio, internet, and a whole lot of other things. So I kind of have developed an interest in how we communicate and the science of it, and so on and so forth, of which there is quite a lot. Years ago, I did a talk on SETI. I had to write a paper on SETI and gave a talk on it, which was interesting. But what I found myself doing, as I said before, was just reciting lots and lots of facts and generally learning the background of it. So I found the background information about it much more interesting than anything else, than the practice of it and the details. So what I'll do tonight is just touch on the history, we'll cover one method in some detail, which is the method that I know most about, which is basically radio. Acknowledge that there are other means of communicating which people who are involved in SETI have considered. I'll try and stay away from some of the more out there stuff. And what I mean by that is that I'll give you an example of that. There is one group of people that have postulated a thing called a Dyson sphere. And if you don't know what that is, a Dyson sphere is where they look for a star system where there's no apparent light coming from the star. And they postulated a culture and a technology developed by a culture so advanced that they've actually surrounded the sun with a sphere, so no one else can see any light from the sun, and they're using all of the energy generated by the star to power their activities. Now that's really off the wall, if you ask me. It was originally proposed, I think, I don't know if it was serious, but it was proposed by a fellow called Freeman Dyson, and it's known therefore as a Dyson sphere. I'm not going to go into that kind of thing. I'm not going to go into that weird end of it. I'm going to try and concentrate on the things that I think are reasonable and that fit in with the normal kinds of communication channels, but the more extreme end of it because of the distances involved. Okay, that's enough of that. Just go through here to, right, history. In 1896, you would have heard of Nikola Tesla. Now, Nikola Tesla was an engineer, stroke, I'm not sure what else he was. He was an inventor, an engineer and an inventor. And he was the first person at least stated that there was an extreme version of wireless electrical transmission that could allow contact with Mars. Now, of course, that's a regular thing today. That's how we run helicopters on Mars. So there's nothing particularly remarkable about that. But it's the first time that I've seen anyone consider the possibility of interplanetary communication using an electromagnetic method. In 1899, he believed that he had detected a signal from Mars because the signal disappeared when Mars set, which means that when Mars went below the horizon from his point of view, the signal disappeared. Now, I'm not sure what it was, and it never happened again to the best of my knowledge, but that was the first actual statement that some sort of extraterrestrial intelligence could have communicated with us. Right, in the early 20th century, Marconi thought he had received signals from Mars and then realized he hadn't. And then in August 1924, the US declared a national radio silence for 5 minutes every hour. The first 5 minutes, the top 5 minutes of every hour during the Martian closest approach. Now, that was the first coordinated attempt. Remember, this is 1924. All they were doing was pointing their radio receivers at Mars at or about the first 5 minutes of every hour, during the time when Mars was as close as possible, and then declaring a radio silence, which is pretty extraordinary. They understood the need or the problem, which is the overwhelming problem with communications at this distance, is the signal-to-noise ratio. And they knew that there was background noise, and this was getting worse and worse all the time. But they realized that this background noise was going to provide, to make it difficult to do this, to receive these communications on the surface and to make sense of them, because they knew that the signals would be massively attenuated by the distance. It's called free space path attenuation, and it's pointless doing the calculation because even with a satellite in low Earth orbit, the attenuation is of order 150 dB just because of the distances, and that's a lot, believe me. You halve the signal every 3 dB, so what's that? It's a lot. It's a huge loss of the signal. When you're coming from Mars, it's massive loss, and when you're coming from outside the solar system, or forget about it, it almost becomes meaningless. So that's the sort of the early history of it. At one point, they used, this was during the radio silence project in 1924. They used a dirigible, lift a large antenna, and they used very long wavelength and radiation because they didn't think anything else would get through the atmosphere, wavelengths of the order of kilometers. Needless to say, they were unsuccessful, not just because there's no intelligence life on Mars, or probably any life at all on Mars, but if they are, they're not going to be communicating with wavelengths as long as kilometers, because the lower the frequency, the longer the wavelength, the lower the frequency, the lower the frequency, the less bandwidth that you have available to actually encode a signal onto the radio wave. Okay, now the modern era. We've done our history now. That's a good history lesson. The first really scientific approach to this was a paper by Cochoni and Morrison in 1959 called Searching for Interstellar Communication. It was in Nature. Now, those of you who don't know, Nature is a very difficult journal to get published in. I mean, it's really amazingly difficult. Only the best papers get in. Only about 1 in 10 of all the papers offered to Nature actually get published. It's a huge boost to anyone's career to actually get a publication in Nature. People usually advertise it all over the place. And it was the first time that a scientific basis for a microwave survey was laid out. And this today is still the basis of most modern surveys. I'll explain why that is in a minute. The conclusion of the paper, I read the paper many years ago, about 30 years ago, and I thought this was a really clever conclusion, because they've said that the probability of success is difficult to someone called Marcus is doing something there. I'm not sure what that is. All right. It's difficult to estimate, but if we never search, the chance of success is 0. Okay, so you've got to try. Now, this is a paper by Morrison, Billingham, and Wolf, which was a NASA report. Wayne, just while we're looking, I've got some red lines that appeared on my screen. I'm not entirely sure what it is.
That's interesting. I don't know how they got there either.
Yeah. Okay. Right. Well, I'll just explain what all this is. This is an impressive looking graph. In those days, this was the early 60s, late 50s, early 60s. They were still observing from the ground. And so they had to consider the terrestrial atmosphere. They had to establish what radiation would get through the atmosphere if they were observing from the ground. And so they looked at all of the means of attenuation of radio waves in the atmosphere. And you can see there that there's oxygen lines and water lines, and there's a cosmic microwave background radiation. There's a thing called the quantum limit that's outside consideration for the purposes of this study. And what they found was that the best window in through the atmosphere was at about the line, which I'll point to now, called the water hole, which is a line formed by a transition, an electronic transition, I think it's a spin flip transition in hydrogen, and another transition in OH. OH is the hydroxyl radical, which is a kind of a pseudo molecule. And there's a range of frequencies there, beginning at 1.42 gigahertz. And that's a wavelength of 21 centimeters. And so they thought, okay, well, if we're going to search, what we're going to have to do is realize that anyone who has established radio communications and who wants to communicate over very large distances is going to need to know what, first of all, is going to understand radio communication. Is going to need to know that these kind of radio windows exist. And if they don't know that, well, they're probably not worth communicating with anyway. But if they do, then by listening in or about this region, it's 1.42 to about 1.7 gigahertz, then that gives us the greatest probability of success. That's the distance that radiation can travel more or less undiminished, or as undiminished as it can be through the interstellar medium and through atmospheres, is at about these frequencies. Anyone who's smart enough to develop radio communication is going to know this. All right. The next order of business was to work out what the probability of success was. Now, this is really difficult. And the first person to do this was a fellow called Frank Drake, who died only a few days ago, actually. He was a researcher, and he decided that he would make some attempt to establish the probability of success. And the reason he did this was that he was looking to use the newest radio telescope in the US, which was the largest radio telescope in the world at the time, in Greenbank at the National Radio Astronomy Observatory, NRAO in Greenbank. So he decided he had to make a science case. Well, he had the science case. The Caccioni and Morrison paper gave him the radio science case. And the probability of success science case was this equation. It's a probabilistic argument, as I said before. What I mean by that is it's just a series of probabilities multiplied together. All right. It can't cover everything because there's just too many things you've got to cover. This is a very, very complex field, and you can't cover everything, but he picked the biggest single contributors, and this he did. And although it's only an approximation, and there's no attempt to arrive at a precise answer, it gives you a feeling for the likelihood of your success. And that's all it is, really just a feeling. And I'll talk about some of the criticism associated with that later on. Now, the equation itself, this is it. You will notice that it's not a very impressive looking little thing. It's just a number n times a whole bunch of other letters. Each of those quantities is just a number. The F quantities are probabilities, and they're expressed as a fraction. So one chance in 100 is expressed as 0.01. Okay, that's how it's numericalized. I'll explain what each of the details are. And each of these quantities is, I'm new to using Keynote here, so I'm going to make a few little mistakes along the way. R star is the average rate of star formation in the galaxy that we're in, where he's only considering this galaxy. And the reason for that is just because of the distances, that's all. Okay, so R star is the rate of formation of stars. FP is the fraction of those stars that have planets. That's a contentious one, and I'll explain why a little bit later on. NE is the average number of planets that can support life. Now, again, that's also a potential one because it depends how you define life. And what I mean by that is we think of life as what we observe, some sort of carbon-based existence with some form of intelligence and, you know, a head, 2 arms and 2 legs, perhaps a torso, or perhaps they swim or something. Legs, a head, eyes. We think of it that way, but it doesn't necessarily have to be that way. And we think of life as something that oscillates around about the melting point of water. So these are some of the considerations. FL is the fraction of those planets that could support life, that actually develop life at some point. And this is where the conditions on the planet matter. Now, when I say the conditions on the planet, it's not just water. We think of life as requiring water, and most of the life, in fact, all of the life, as we understand it, does require water. This is where you can get all philosophical if you want to. But it's more than that. There's an awful lot of radiation out in space, and that radiation has to be shielded from the surface of the planet. The temperature has to oscillate in a range that we think is acceptable, where liquid water can exist on the surface. There has to be an atmosphere for them to breathe, or water on the surface, which would also require an atmosphere to keep it there. And that atmosphere has to be protected from things like the solar wind. The atmosphere on our planet is protected from the solar wind by the geomagnetic field, the same magnetic field that makes compasses point north. If we did not have that, because we have a metal, a spinning metal core, then we would not have that magnetic field, and we would end up like Mars, where the atmosphere gets blasted off the surface, or the atmosphere would have to be so heavy like Venus that it probably wouldn't support life as we understand it. So this one here is not such an easy one to tie down. Fi is the fraction of planets with life that go on to develop intelligent life. In other words, that form civilizations. You can speculate till the cows come home about that one. I won't go into that now. And C, F sub C, is the fraction of civilizations that develop some form of communication system and which release these detectable signs of their existence into space, whether they mean to or not, but probably because they mean to. And it's an active SETI. Active SETI is where you transmit into space looking for people. Passive is where you just sit back and listen quietly. And last of all, and this is a very good one, is the length of time for which these civilizations release detectable signals. So now we have to start thinking, does the development of intelligence necessarily guarantee longevity? And my feeling on that is 50-50. I don't know if it necessarily does that. If you want to be pessimistic, then you're probably never going to be able to communicate with everybody, because there's a real probability that intelligent life will form and destroy itself unless it also develops sufficient maturity to understand what it's doing before it destroys itself. So again, speculate till the cows come home. An estimate. Well, we know our star pretty well. It's about 1.5 to 3 per year. That's the number of stars formed per year in our galaxy. The FP is the number of solar systems that can develop planets. Now, about 2/3 of all of the solar systems in the galaxy have more than one sun in them, polysolar solar systems. Unitary solar systems are much more stable. One of the things that life requires is long-term stability. And the reason for that is that life happening and intelligence happening is a largely, it's an accident. And if you have enough time where the planet is stable enough and safe enough, then an accident will form and life and intelligence will form pretty much as soon as it can. Certainly life will. I don't think there's any doubt about that. Whether it goes beyond that depends on how much time it has. The reason I've picked the figure of 0.3 here is that about 1/3 of all the planets, the solar systems, have only one sun in them. And the advantage of that is that the likelihood of an environment, especially the thermal environment, on a planet being stable for long periods of time is greatly enhanced if there's only one sun, because the orbit that the planet will be in is much more stable, much more circular. Whereas if there's more than one large sun in a solar system, the orbit of the planets is going to be very complex, and the likelihood is that the environment on the planet is going to fluctuate enormously, and that'll make it much harder for life to form, at least as we understand it. Right. NE is hard to estimate reliably, and I've picked a figure of 1/100th to 1/10 of all of the planets. The life factor is similarly 0.01 to 0.1. In reality, that could be much less. It's a difficult one. It's a reasonable estimate, though, that I've made here. I've estimated into the middle as much as possible. Intelligent life can form about 1% of the time, 1/10 to 1% of the time that life forms, I think. Communication, and here I'm being optimistic. If we get to the point where intelligent life forms, I'm going to optimistically assume that the probability of being able to communicate with them is 1. Now, that might be overly optimistic, but I don't think it is, actually. Now, here's the really difficult one to estimate. If a society lives for 10,000 years, that's 10 to the power 5, then that's about the same as our society. We've lived for about 10,000 years, but not while we've been technologically effective. And what I mean by that is that we haven't had electronic communications, electromagnetic communications for 10,000 years. We've had it for about 100 or 120 years, something like that. If we keep going as we are, and we've had 10,000 years of electronic communications, then we are probably going to be able to communicate very effectively with the galaxy. But it could be even longer than that. And 10 to the 7 is 10 million years. So that's the range I've assumed for that, for the purposes of this analysis. N, if you work it out, thus turns out to be ranging between 4.5 by 10 to the -3 to 9 by 10 to the +3. So that's quite a huge range. That's the variation of N. And why that's significant, the implications of that are simple. A figure greater than 1 implies that there is other life in the galaxy. And the results of this analysis oscillating about 1 means we're on the cusp of it. So I don't know. Some estimates range much more widely than mine do. Frank Drake, the person who actually came up with this equation, estimated something like 100,000 or 1 million intelligent life forms in the galaxy. Now, I think that's woefully optimistic. I've seen figures that I believed anyway, where the implications were pretty good, that there are between 10 and 100. And I think that's not reasonable, not unreasonable. And that means that we're in the game. There's probably intelligent life out there. We haven't heard from them yet, but it's probably there. But the equation also attracts some criticism, and we've got to talk about that too. Many of the numbers are highly conjectural. We've talked about that. You can see that. And that's largely because they can't be tied down very accurately. They're concerned only with radio and electromagnetic communication. Now, There are, of course, other ways to communicate. I don't know that they are effective. One of the potential methods of communication, which is on the fringe of being considered at this time, is a thing called entanglement technology. Now, quantum entanglement is a strange concept where it would appear that any two particles which at one time in their existence are close together and then are separated remain in a way somehow linked and are instantaneously able to communicate their states to one another. It's not clear exactly why this is. Einstein used to call it spooky action at a distance. Well, that's exactly what it is. It's spooky. We don't have a reasonable answer for it yet, but it's instantaneous. So that's a non-electromagnetic form of communication, but it's so far beyond what we're capable of at the moment that I won't consider that, and that the equation doesn't consider that either. It's a series of multiplications, and the outcome of the factors is very large, as we've observed, that it's difficult to draw any conclusions. So it's always speculative, and I think it was always going to be. And this is the big one for me. No consideration is given to simultaneity. And what I mean by that is it's all very well to say that a galaxy which has existed for the best part of 5 to 10 billion years could have hundreds of intelligences in it. But did any number of those intelligences happen to evolve at around about the same time? And that's a problem. The equation makes no consideration for this. It's probably trying to take a snapshot of the situation as it is now. But once again, that's a shortcoming. So then he went ahead, this is Drake, went ahead, and we get now into the beginnings of the modern era, the first surveys to be done. And he created a thing called Project Osma, which consisted of the first survey out the 21 centimetre hydrogen line, this so-called water hole that I explained earlier on, and searched two stars. There's two star systems, Tau Ceti and Epsilon Eridani. Now, they seemed like likely candidates. So he searched those with the NRAO telescope using a 400 kilohertz single channel with 100 hertz wide resolution. Don't worry if you don't understand what that means. I'm going to explain that in a minute, okay? That means that they looked for communication in or around that 1.42 gigahertz frequency and split up the channels that they looked at down to 100 hertz at a time. That's not very much. That's a very narrow band. And as I said, they used the 26-meter telescope at Greenback, which at the time was the largest in the world. And the observation duration was 150 hours. Now that's meaningless. If you are fantastically lucky, you might have nailed it, but really 150 hours of communication where you're talking about 5 billion years of evolution is really, it's a token event, but it was the first one. I could now list hundreds of possible attempts, and this is where I could put you all to sleep in no time at all, but I'll talk about one or two. And there's one called the Big Ear. This also happened before, actually, before 60s. They used a specially built radio telescope array. It was quite small, but they kept going with it until 1977, and they produced a very widely publicized what they believed was a detection. Whenever people do these studies, they always come up with some form of detection. Somebody, almost everybody who has ever done one of these studies have found an interesting signal. But this one was very interesting because it's known as the WOW signal. It was part of the Ohio State SETI program, as I said before. And they received a signal, and this is the piece of paper with the printout. It was done on, there was no graphical details then, it was just numbers printed on paper. And they were so amazed at the scale of it that he just wrote the words WOW on the paper next to it, and it became known as the WOW signal. But it never repeated itself. And that's one of the things about any kind of scientific measurement. If it doesn't repeat itself, if it's not repeatable, then it's not a reliable measurement. more than one person has got to be able to hear it or see it or repeat the experiment and get more or less the same result. This was interesting, but it never came back. So now I'm going to just talk for a little while about different strategies. There are two basic strategies to electromagnetic studies. There's a targeted study and a sky survey study, and the two studies have two basically different philosophies, and I'll use an analogy if I may. Just imagine that you've established that you know which field that you're going to dig in. You're going to look for gold, and you've established that somehow that there's a field out there that you believe gold is in, but you don't know where in the field the gold is. You can dig a series of targeted holes quite deeply and look for signs of the gold, or you can take the top of the field, which is quite shallow, and look everywhere in the field. Okay, so you can do a broad, shallow search or a targeted deep search. The problem with the targeted deep search is that you might drill a hole and miss it. And the problem with the broad survey search, which is quite shallow, is that you might not go deep enough. So both philosophies have advantages and disadvantages. A targeted search is looking at a specific region or objects, and a good example of this is Project Phoenix. It's run by Professor Jill Tarter. Jill Tarter is one of the leading lights in SETI, and she actually gave a talk at Sydney about 10 or 15 years ago. She came out from one of the science schools. A survey search looks at the whole sky, and a good example of this is Project Beta, run by the Planetary Society, which was set up by, among others, Carl Sagan. The survey search algorithm depends on very high spectral resolution. I'll explain what that is in a moment, and very, very, very large loads of data analysis, and I'll explain that in a moment. Surveys also need to take great care to account for Doppler shift. And what I mean by that is, when a radio source is moving towards you, the signal from it is shifted up a bit towards the higher frequencies. When the source is moving away from you, the signal is apparently shifted down a bit, or red shifted. Blue shifted if it's towards you, red if it's away from you. Some astronomical objects astronomical sources, that's the best way to put it, naturally are rotating objects. And if they're rotating objects, for a time they'll be moving away from you, for a time they'll be moving towards you. And you'll see a regular variation in the frequency, and you have to account for this you have to understand enough about the Doppler shift to account for this. Otherwise you could end up mistaking it. A survey search must be carried out with limited resources. And the reason for that is that the search area is so large. That's another disadvantage. The survey method is thus time limited because you need a lot of resources and you can't use them all the time. You just have to occupy too many of them. So you've got a limited amount of time. A targeted search can spend much longer looking at specific sources because you have a specifically designed piece of equipment, the radio telescope, whatever it is, which you're using to look at the source. And the advantage of this is that you're much less time limited. You can spend a lot more time, and many of the projects that are targeted have been running for many years, even decades. That's a good thing. Now, search sensitivity. This is a rather busy graph. I'm sorry about that. You'll see that there are two vertical lines on that. One of them says SS and one of them says TS. The SS is the sky survey and TS is the targeted survey, targeted search. Depending on how much power the distant civilization is using, the different searches give you access to different numbers of potential stars and potential civilizations. So if we're talking about TV leakage, which is, perhaps a few million watts, you might conceivably miss it. I don't think there's any reasonable way that you could get to that with either search. If you're talking about a gigawatt of transmission, With a targeted search, if you happen to be lucky enough, you can see that there's, I'm not sure if I can move the cursor here, no, I can't. You will see that there's a point where the TS line crosses the 10 to the 9 watt line. That gives you anything up to 10 stars, which is a lot. And you're talking about a targeted search. If you take 1,000 times more power than that, that same style of survey would give you anything up to close to 1 million objects because of the distance that you can see into the distance into the galaxy. If it's using about 10 to the 13 watts, which is about the power used by the Arecibo radio telescope, even a sky survey search would give you access to perhaps 10 or 100 objects. And if it's 10 to the 15 watts, that's an awful lot. That's a petawatt. You might, even with a sky survey, you might get as many as 10,000 stars. By the way, EIRP is effective isotropic radiated power. That means that you're not really using 10 to the 15 or 10 to the 18 watts, but you're concentrating the signal in such a way that it looks like you are using those sorts of power. So you don't actually have to have transmitters that generate power. You just have to have very high concentrating antennas like the one at Arecibo used to be, which of course isn't anymore for obvious reasons. Right. Now, signal identification. I said before that I could just rattle off information about the signal identifications and the power and the number of and the channel widths and so on and so forth. But rather than doing that and put you all to sleep, what I'll do is try and explain, this is the science of it that I promised before, how you analyze a signal. What you do is you measure a signal, and this is just an arbitrary figure, a signal of some sort every 3 years, a smaller signal every 4 years, and a much larger signal every 6 years. And how the timeline of that would look is what you see on the graph, okay? And imagine a wiggly line connecting the peaks of each of those lines. So that would be a line up and down all over the place. If you were looking just at that line, if you recorded that information, you wouldn't really be able to tell anything about it. So what we do is we do a little bit of mathematics on it. Some of you will already know this, some of you won't, so I'll explain it, which is referred to as a Fourier transform or a power spectrum analysis. And I said before that there's a signal every 3 years, 4 years, and 6 years. What the power spectrum analysis does is change that x-axis, the lateral axis at the bottom, the time axis, into a frequency analysis. And what you'll see there is that there's a very large signal at around about 0.16, 0.17, that's 1/6 of a year. That's the frequency of a signal that appears every 6 years. There's another peak at around about 0.25. That's the peak of that's the signal that appears about every 4 years. And there's another peak at about 0.33. That's one that appears every 3 years. So you're looking at a spectrum that gives you the frequency of an event happening. Okay, now I'm going to talk about a few other things in a minute, and then I'm going to actually engage in a little SETI survey here right now as we actually do this talk. We are actually going to look for alien civilizations tonight. We are actually going to see that. I don't anticipate that there's a very high probability of success, but I've explained something just then, and it needs more. You need to know the implications of it. So I'm just going to shut down the presentation now, and I'm going to do something else. Oh, now this, I don't know if you can see it, is a small radio. Okay, it's called a software-defined radio. I borrowed this temporarily from Eva's laboratory at the university today. I don't know if you can see it or not, but there's a little silver plate there that covers a silicon chip, which has under it a logic gate array called a field programmable gate array. And I've connected that to some software in this computer, which I'm going to use to run it. And then I've connected it to a very high-tech antenna. And this is that high-tech antenna. It's a little wire and a biscuit tin. The biscuit tin acts as a ground plane. Okay, now, as you can see, it's not a very sophisticated antenna. So the probability of success is pretty low, but it makes the point about what the data looks like from this. So what I'm going to do now is just momentarily run this. Just bear with me. And what I'll do is, oh, where are we? Back there. That's right. Okay. Now, what I'm going to do is, Wayne, I'm going to need to share this screen. Oh, there it is there. Sorry. Okay. Share the screen, and there it is. Okay. No, that's not it. That's it. Can you all see that screen? Just wave your hand if you can. Yes? All good? Right. This is a real-time signal from a radio. So this is what people who are doing SETI searches look for. This is more or less what they see. We are now listening for a signal at 1.42 gigahertz through that little radio that I just showed you then. And the line at the top is the raw signal, the voltage or the time base of the signal. You can see that pulling a frequency out of that is going to be somewhat difficult. The figure at the bottom, the graph at the bottom, is the power spectrum analysis, and it's a frequency. And what you can see is that the frequencies, I hope you can see, the frequency is in megahertz. And although that doesn't show very much, if you look carefully, I don't know if you can see this, but there's a peak there at around about 800 kilohertz. A bit more than 800, about 810 kilohertz. So that means that there is a signal being received by that little antenna on my desk over there at around about 800 kilohertz, with a signal on top of the signal, which at 1.42 gigahertz, which is what that's listening to. Now, is that intelligent life? I think it's most unlikely, but it shows you that this messy signal that you see here can be distilled into something that we can see here. There's an electrical disturbance somewhere in my flat or in this area that runs a signal about 0.8 megahertz over and above 1.42 gigahertz. So that's a signal that's on that frequency, but I don't know what it is. It's just a signal. It's interesting to note, we've picked it up, but when people are doing SETI searches, that's what they're looking for. They're looking for a signal like that, just a peak in a bunch of wiggly lines that appears out of the background and appears persistently and continuously. Or it might be intermittent, and if it is intermittent, that's fine, but as long as it comes back again, so it's repeatable. Okay, so there's our little SETI search. I think we can safely say we didn't find anything, but it was interesting. Right. So we shut that down. Right, now we'll go back to the presentation. Thank you for bearing with me with that. Right, so knowing now what they do, one of the more modern arrays, let's see how we're going with this. Yeah, doing right. One of the more modern arrays is a thing called the Allen array, which presently consists of 42 dishes, which look pretty much like the one you see there. It was mostly funded by a fellow called Paul Allen, who was one of the founders of Microsoft. He was the Bill Gates partner. And they're working on this at the moment. They intend to have 350 antennas, but there's no sign of those appearing at the moment. And this is where you need to know about that graph I was showing you then. It surveys it's one of the broad surveys. They're going to look at the galactic plane. They're going to look at 40,000 million objects, 40,000 million frequency channels with a bandwidth of 0.7 hertz. So if you remember that little graph we showed just then, 40 billion of those, each one of those split up with a bandwidth of just 0.7 hertz. And the reason they do that is they're looking for any tiny little signal at all. And that's the scale of what they're able to do with modern communications. And I could go on for ages about how many of these things, surveys have been done and how many channels they have and what the bandwidths are. But now you know what I mean. It's a boring thing to talk about, but it's the way you do it. It's the kind of commitment that you've got to go through to actually give yourself any reasonable probability of success. There are even larger surveys. There's an old VLA. If those of you that know the VLA, I'm sure many of you do. It's called the Carl G. Jansky array now. Have been looking at evidence of extraterrestrial data. In the last year or so, this array has been updated to scan lots and lots of millions of, I'm just going to have to move this. Right. Millions of stars in the Milky Way. And this thing, it generates an enormous amount of data. And then therefore the analysis of that data has to be done for it to be meaningful. And the reason that that's an issue is that I just did one channel with a bandwidth of about a megahertz or so, and that began to stretch my little computer here. Imagine having to do tens of millions of channels with tiny little resolutions. And so you run into problems with computing power, and that's where SETI at home came along. It was basically crowd supplied computing. And that's how much of the data is crunched, although they have some pretty impressive computers these days that are specifically designed to do that. And the limiting factor for the whole thing then becomes data analysis, both the time and the computer power to be able to do it. With the VLA system, what they've done is install a splitter that takes the data off other surveys that the array is doing. In other words, then it's not a specific SETI survey. That's a great thing to do because it means you're actually using the array for two different things at one time. And it costs so much money to do this now that I don't think there's enough probability of success to have dedicated arrays unless they're privately funded, like the Allen array. So using piggybacking, so to speak, off existing arrays like this means that you don't waste money and you can still look at hundreds of millions of frequency channels, but it all is limited by the amount of data analysis you can do. Right. Very small point. How do we know it's alien? Okay. Radio communication is a funny thing. It's one of the few natural or phenomena in nature which operates in clear, discrete integers, numbers. Okay. So if I generate a frequency of 1 megahertz, there'll be multiple frequencies further up the scale at even multiples. Like there'll be a signal at 2 megahertz and 3 and 4 and 5. These are called harmonics. And it's the nature of how the signal is generated. It's a side effect. Not entirely unlike a guitar string. If you pluck a guitar string, you'll produce a bass note, or a fundamental as it's called. And you'll also produce a series of harmonics further up the chain, which are exact multiples of that frequency, which musicians call overtones. And it's exactly the same as that. You always produce more data, more signal than you want. You try to limit it, but you always do produce some of it. But if you multiply that frequency by an irrational number, a number which absolutely cannot be an integer, like pi, for example, then the results of those harmonics will be at multiples of pi, and pi is not a rational number. That means that it can't actually be tied down accurately. and it can't be a naturally occurring phenomenon. It would have to be artificial. And that's one of the ways they know. The same is true of multiplying by 2 pi or the square root of 2 or anything like that that's an irrational number. That's one of the ways we could distinguish between what looks like a random signal and something produced by aliens. Costs, right. Now, the SETI Institute costs about $10 million a year, $2 million a year to run. The cumulative costs of all SETI programs are estimated at 10 times that. So there's a significant amount of money involved here. And when you think about it, that money could be doing other science, could be doing some really worthwhile science. So to spend it on something as speculative and unlikely to succeed as this is a pretty impressive commitment. Some of it's private money, which nothing we can say about that. If people want to spend their own money on this stuff, they can do that. But for governments to be spending their own money on this without getting something else out of it, like a piggyback search, is a frivolous thing, I think, to do. So I'm glad they don't do it. A quick note about other technologies. There are also some searches in the optical. And there's a project, I think it's Princeton, where they're using a 1.8 meter optical mirror with a whole series of photomultiplier tubes with measuring very, very fine angular diameters, 1.5 arc minutes on a side. That's a very, very narrow field of sky. And with 64 photomultiplier tubes doing this, and in 2 planes of polarization, so like that, looking at it that way and looking at it that way. And they can cover the entire northern sky every 150 clear nights, so that they can get a lot of information, and they're looking for things like lasers. This has only been possible since we've realized that lasers are possible and that high-powered lasers are possible. And the advantage of that is that they are very, very directional. Okay, that's one other possibility. And the last point I want to make is a thing called the Fermi Paradox. Now, the Fermi Paradox was something that was produced, which was put forward by Enrico Fermi. He was a great physicist. He's one of the people who worked on the Manhattan Project. He was Italian. He also discovered a lot of the early, what are called transuranes. That means elements that are larger than uranium, which were one of the great holy grails of particle physics in the early days. And he also was the first person to run a nuclear reactor in Chicago in 1943. And he made a statement that goes like this: the size and the age of the universe make us believe that the technological advanced civilizations must exist just on the rules of probability. But this seems to be logically inconsistent with our lack of observational evidence to support it. Okay, where the bloody hell are you? That's another way to say it. 1, our assumptions used in estimating the number of civilizations is optimistic. We've touched on that. And intelligent life is much rarer than we believed or would like to believe. We're using the wrong techniques, or we haven't been doing it for long enough and it's just too early to say. Our survey algorithms are flawed somehow, and that we're not looking in the right place, or in general not looking at the problem the right way. And somewhat pessimistically, the other possibility is that it's in the nature of intelligent civilizations to destroy themselves. I certainly hope that the latter one isn't true, although there is some evidence to suggest that it might be. We can only hope for the best. But if we never try, we'll never know. So that's it. Thank you all for listening.
Thanks very much, Tony. I think if you look through the comments, actually, Scott's made an interesting one about the.
Sorry, I hadn't looked through the comments yet.
Oh, it's okay. Most of them weren't really that, but Scott put something in there about the Drake equation.
Yeah.
So if you scroll, I'm really not going to read that out. It's a little bit too long.
Oh, yeah, that's a good point. Yes, I've got
Yes.
that one. You're right. It took about 1 billion years, but that was only because there were several interruptions to that. And what I mean by that is, yes, multicellular life evolved more or less as soon as it could. But in those days, this is billions of years ago, the environment in the solar system was pretty violent. There was still a lot of residual stuff flying around, banging into planets and destroying life. So a lot of time, I think it's fair to say that life started lots and lots of times. What we don't know is what the last time it started, how long it took from the last time it started. So that's a good point. But the difficulty with it is to know really how long it took, because there's a possibility that it took less than we thought. So you're right about that.
Thanks for that. I was sort of leading up more to the second part of the commentary there, which is, yeah, okay, life forms takes time. Intelligent life forms, if you want to include animals as being intelligent, but then to skip from, let's say, animal intelligent life to a form of intelligence that can communicate only happened in, let's say the last few years. When you look at the Earth.
About 100 million years, 150 million years, something like that.
But then for civilization to get to the stage of being able to communicate, that was only very recent.
Yes, it was. Yes, about the last 100 or 150 years.
Yeah.
It tends to be what they call a hockey stick curve. Things sort of gather momentum and it all goes at once. So yes, you're right. It takes a long time to happen. When it happens very quickly though.
Mm-hmm. Okay.
Any other questions?
I was actually going to make a comment about the Fermi Paradox that you put at the end there. In many ways, I would think all of those four things are probably true.
All of them are
probably, which is the worry.
Yes.
But I think that to us, in a sense, all four are affecting the result. And the other thing I was going to say is that realistically, isn't the problem that we don't have enough people doing the actual survey at the moment, searching for the signal?
Well, the problem is it's just too early to say. Yeah, that's the answer. And that's one of the advantages of the piggyback search, is that you can use virtually every radio telescope in the world.
Yes.
And record data from it by using a splitter. And the problem then isn't the amount of observing capacity that you've got. The problem is the computing capacity. That's the rate limiting factor.
Yeah, I would think that that's true, because we don't have the computing capacity at the moment to do the type of search, which may be out there, but we've not seen it because we just have not got enough things up there looking for it.
Yeah, but quantum computers might be the answer to that, Wayne.
Yeah, well, I think maybe then in 10 years we will have the technology, and then it's going to be a bit more serious.
It won't be 10 years, Wayne. It'll be longer than that. Sorry.
Right. Okay. I was being optimistic then.
Yes, you were. Yeah. It's a bit like fusion energy. When I was a student at university a long time ago, about 40 or more years ago, fusion energy was 30 years in the future. We won't have any problem with energy. We won't even bother having electricity bills. We'll be able to generate so much energy. Yeah. Where are we now? Probably about 40 years in the future, we'll have all the energy we want. Right. Wake me when it's ready. I want to know.
Yeah, the trouble with fusion is that to try to get the components that create fusion energy, there's not too many places we can find helium-3.
The situation with quantum computing, Wayne, is the same in the sense that it's inherently hard to tie down. It's not hard to build a quantum system. It's hard to communicate with it and program it. That's the difficulty.
Oh, okay. I see what you mean, to do something like
even if you can build a quantum computer, how the hell do you program it? I still don't know it's done yet. They haven't said there's a lot of ifs about that one, but anyhow, let's not speculate too much about that.
Wayne, if I may make a comment.
Mm-hmm.
Yeah, Tony. I mean, I a lot of the observations and assessments that you presented us with tonight really are quite profound, and I've thoroughly enjoyed this. But it seems to me that, to your point earlier, our technological civilization of a century, or maybe a couple if we include the Industrial Revolution, measured against the backdrop of the age of the universe, even the age of their solar system, coupled with the explosion we are seeing right now in knowledge and in technology, you know, it just, you know, it forces the question, where will humanity be if we don't destroy ourselves in only 100 years, for example?
Yeah, well, that's right. There are two things about technology: your ability to develop it in the first place, which happens very quickly, and your ability to cope with the consequences of having.
Yep.
And so the two things, we tend to be good at developing the technology, but bad at understanding what the
Yes.
consequences of it are. That's the problem. And that's the point 4 there about do we naturally always destroy ourselves because we don't get smart enough to cope with how smart we are. I don't know how better to say it than that. Yeah, you can philosophize till the cows come home.
Yeah, it's certainly a cornerstone of this. About 10 years ago, I listened to an address by somebody in SETI. There's a name that I've forgotten that you'll know. There's a man who's that's the guy.
Yeah.
And he said, this would be a decade ago. He said, at the rate we're pouring resources at SETI, he felt that within about 4 decades from 10 years ago, we'd be in a position to say there is or isn't, some alien intelligence. But I've not heard anything further to that.
It is, but the problem with that, Alan, is that we still haven't dealt with the problem of simultaneity. There's a very real possibility that intelligent life has existed and will exist, but does it exist now?
Yep.
And there's no consideration given to that in our realistic analysis.
And if I can make another comment, I think there's a couple of I think there's a couple of interesting things that could happen whether we find life or not. Personally, I hope we do find life.
So do I.
But if we don't find life, that would mean, okay, so maybe we haven't searched enough. Okay, let's just put that aside. But maybe there is not intelligent life within a communicatable range and at our time span, as you're indicating. And the really sad thing is, I think humanity would go, oh yeah, so what? I don't think the bulk of humanity would say, we are special, our planet is special. I think they'll just go, so what? And I think that is a great pity.
Well, no, I think the opposite would happen there. It's not so much, I think that there are enough people in the world that think that we are special. That's the problem. It's not the people who don't think we're special, it's the people who do think we're special. And the other possibility is, what is the probability that people will react to it in a negative way? And there's enough nutters out there, who would elect an orange-faced moron to the presidency of the most powerful country on earth. Not just Americans, but they were in this case. To give you a pause when you think about what would happen to them or people of that ilk if they were suddenly confronted with real evidence. Firstly, would they believe it? Usually they don't. Science is just an optional thing. It's a political point with them. You can even convince them not to get vaccinated. Even people I know who I would have thought were actually quite intelligent will believe all this weird stuff. And if they're suddenly confronted with the possibility of this, how will they react? And the answer to that is somewhat disturbing, I think, to think about. So that's my point on that. I don't want to concentrate on the negatives. I'll try and feel happy about it.
Can I just suggest dark matter? I mean, that can really let your imagination run wild a bit here. What advances are happening with finding out what dark matter is? It may suddenly open up a whole vista of new dimensions, and we may be some very low life that haven't evolved to get the receptors of whatever the other life forms.
You're right.
Dark matter.
Dark matter is something that is more significant outside the galaxy, because that has implications on the whole universe. That's really beyond what we can talk about here, because it's probably dark matter and dark energy that are responsible for the rate that the universe appears to be expanding. But we're talking really now, we're trying to restrict ourselves to the Milky Way, because that's all the technology we understand at the moment. So yes, you're right. Dark energy and dark matter could make things very different if we understood.
Is there work being, I'm sorry, maybe I shouldn't really put this to you, expecting you to answer off the top of your head, but like work on dark matter and dark energy, is a lot of being just, that's just a
vast amount.
speculation at this stage, or they actually try to
Yeah,
investigate?
there's a vast amount of work trying to understand it, but it's very difficult to gather information. It's really only been it's really only been touched on with any level of even partial understanding in the last 20 years or so. So it's still early days. And I'm not an expert at that. You need to talk about someone like Grant Lewis at Sydney University or something.
Oh, he's getting a lecture at University of New South Wales tomorrow night, I think.
Yeah, if you do so, he's a very good lecturer.
I think it was actually Wednesday night. I'm not sure if it's tomorrow night. But
You're right. Yeah, Wednesday. Sorry, Wednesday. That's right. I put up my diary Wednesday.
Carl works with him. Carl Kuznitsky works with him a bit. So, okay, Wayne, that's me done.
Well, thanks very much, Tony. It's certainly been the way you've tried to explain it. I really like, because I hadn't think I've seen anybody plug the numbers in for a while, certainly, but it does show that the range in itself means that there's very likely versus not likely, and I think that it's probably a little bit narrower than what the Drake's come up with, I think, which was really wide.
All of the estimates seem to hover around 1.
Yes.
It's kind of annoying in a way. It gives you no clear result.
No, very, very convenient, I suppose, is the words we'd use then for. But I also think that technologically we may not be there at the moment to get the information, and I think that's the worry. And the other possibility, of course, is that the people that we might be trying to communicate with, because of some of the other things we're touching on earlier, like even we work in, say, 4 dimensions, one of which being time. What happens if you then got civilizations that operate outside that number of dimensions that we're operating in?
Yeah, you're getting out into the speculative world there, Wayne.
That's the problem. That's the problem.
To limit this to what we understand the technology is capable of now.
That's right.
If other technologies comes along that makes it better, well, like for example, this quantum entanglement thing, then great, but I can't speculate about that because we just don't know enough to do it.
No, and certainly whatever we're looking for in terms of life, we don't think that there is any life like intelligent life inside the solar system anyway. What we're looking for is outside. I think that there's been enough research even done at the moment looking on the other planets that we've got. As you know, the Goldilocks zone and things like that, as to what you're going to find, what we think is we're going to get intelligent life from. There isn't anything in this solar system for it. So we've got to look outside.
We're the only planet in the Goldilocks zone as we understand it. That's where we're talking about liquid water.
That's in fact what the search for exoplanets is all about too, what we're even relating to this. When they come up with more of them that might be suitable, that also helps the potentially SETI sites that they might want to target.
There's definitely a few planets in the Goldilocks zone out there. There's no doubt about it.
Yeah. Okay, well, thanks very much, Tony. It's certainly been thought-provoking, which I think is the way that we needed to look at it. And it's been a little while since we've done anything like this, and I appreciate the time you've gone into to do the research. And I know it wouldn't have been trivial for you, so much appreciated, Tony.
Brilliant. Problem.
Thank you, Tony. So what I'd like